So hi everyone, I'm Freddy. I work in Element AI, and Element AI is quite a big company. It's about 500 people based in Montreal. But I'm part of a very small team which is based in London, about 10 people. And in that team, we focus on AI for good. So we don't focus on commercial projects. We partner, instead of commercial clients, we partner with nonprofit organizations and NGOs. And we're going to focus on a partnership that we've done with Amnesty International, specifically on the toxicity on Twitter and the abuse against women on Twitter, and also the protection of human rights from satellite imagery. So some of the content in this presentation will be quite explicit, and I will give you some warnings, and if you feel that you're easily triggered, then don't read the content, okay? I will not read it out loud for you for obvious reasons. So first, I'm going to talk about the toxic Twitter campaign that Amnesty International has been running for several years. And then I'm going to talk about how we bring our technical expertise to their domain expertise to further amplify the campaign that they've been building momentum with for several years to change the policy of Twitter in protecting their user base. And in particular, protecting women's rights to be heard on Twitter. And specifically, we're going to focus on a cohort of women politicians and journalists in the UK and the US. So I'm just going to play you a very small segment of the video just to kind of set the tone so you know what I'm talking about.
Speech. It's not free speech.
Oops. Okay, let's try that again.
Death upon me.
Twitter has changed the 21st century. It's rocked so many lives, changed the way organizations run, how we hear the news and how we operate and connect with different people. That's amazing. And I totally get that Twitter is about freedom of expression. But if women can't be free to express themselves, there's a real problem and Twitter needs to address it.
If people said to me the things they say to me on Twitter in a public square, that would be harassment, right?
This is how institutional racism thrives. This is how institutional misogyny thrives. This is how institutional xenophobia thrives. And this is how queer folks, people of color, feminists, trans folks, all of us are discriminated against because these are people who have these thoughts and they're able to freely spread them on Twitter.
If Silicon Valley can invent a self-driving car, they can figure out how to address the abuse on their platforms. They just have to care about it enough.
Well, I see where she's coming from. It's really not that simple. If anything, that's really a sign of the kind of a myth that Silicon Valley is built around AI, and people believe that AI can do anything, right? But that's very much not the case. So let me tell you a little bit about what Amnesty has been campaigning for. So Amnesty campaigns, well, they believe that women, they deserve to be on Twitter, they want to be on Twitter, they deserve to be heard without being harassed and abused. And Twitter does have a human rights responsibility to their user base. In the same way that people going out in a public square and being able to be heard have a human right not to be abused and harassed. And there's also, they're campaigning for more transparency in the platform. So, once you report something, once you find something which you find abusive or someone who harassed you, the only means you have to tackle this is by reporting it on an individual basis. But that doesn't really scale up. Now, if you're a public persona, for instance, and you receive hundreds of abusive tweets, you just don't have the time and you don't have the mental health capacity to tackle each and every one of those harassments, right? And also, so what Amnesty suggests is some mechanisms that allow the user base to protect themselves more easily. So something like some kind of alert, similar to something you get in your Gmail, for instance. Your Gmail says, this email is probably important, you might want to read that first. Well, why doesn't a similar mechanism for tweets also exist that says this tweet is very likely to be threatening, so you might not want to read that? Amnesty is really good at running campaigns, and they're really good at raising awareness of social issues. So one of the things that they've been doing is they use famous women journalists and politicians as examples of excessive harassment. So for instance, one of the most abused women politician in the UK is Diane Abbott, and she's known for receiving thousands of abusive tweets, and yeah, she even had to take time off because her mental health suffered. So what did we do to, how did we, when we brought our technical expertise to Amnesty, we suggested to run a crowdsourcing experiment. So we designed a study where we selected a cohort of women, about 800 women, politicians and journalists in the US and the UK, and then we said, let's download all of the tweets that mention them and ask the volunteers of Amnesty to make an account on something called the Decoders platform and annotate tweets. So this is what the platform looks like. So a user, a decoder, as we call them, looks at a tweet, and I'm gonna now unblock that. So looks at a tweet, and it's completely anonymized, so the ID of the abuser is removed, of the potential abuser is removed. And then they're asked to annotate it as 3 levels, 3 classes. Abusive, problematic, or nothing at all. If they think it's problematic or abusive, then they're asked to categorize what type of abuse it is. So this is what the UI looks like, and this is how we collected the data. And the data we compiled amounts to about 150,000 different tweets across this cohort of 800 women. Okay, and then we did a study. So this is a study that is called a large-scale crowdsourced analysis of abuse against women journalists and politicians on Twitter. So this is something that we published at the New York's workshop on AI for social good last year. And it's been in collaboration with my former colleagues at LMNEI, Laura DeLeo, Christoph Anjuski, Archie de Berker, Milena Marin, and Julian Kornebisch. So Milena Marin is our liaison from Amnesty, and she co-authored this paper with us. And this whole idea of using a decoders platform to annotate whatever problem they might need annotating with. So this was her idea, actually. And they're not just using it for Twitter, they're using it also to annotate, for instance, satellite images of destructions in Raqqa from the US coalition, or annotate the human presence of villages in satellite tiles from Darfur, for instance. And I'm going to touch upon that on my second part of the talk. Okay, so maybe I can show you some results here. And again, some of this content might be quite triggering. I'm going to show you some very explicit examples of the types of abuse that annotators encounter during this crowdsourcing. Okay, so I'm not going to read it out loud for obvious reasons. You get the idea, okay? And because we also collect the metadata, we also know some metadata about each subject in the cohort. For instance, we know what country they're in, their racial background, profession. Now we can ask very specific questions about specific demographics of how much abuse they encountered based on what the crowdsourcing army perceived. Okay, so for instance, if you look at these questions that kind of breaks it down across race, we're saying, so the blue bar is the problematic category, and the red one is the abusive category. So what it says here is, you got 5.6% problematic. So 5.6% of the tweets that were mentioning the white women were deemed problematic by the decoders. And 1.2% was deemed abusive. Think about that. 1 in 100 tweets were abusive against white women. Now let's see what that looks like for Latinx. So we get 4% and 0.8. And by the way, these black bars are confidence intervals, right? So this is something that you acquire by bootstrapping. And they're basically telling you what is your error margin. They're 95% quantile intervals. And they tell you what is your error margin in your estimate of the abuse rate. And this is the rate for Asian women. This is the rate for mixed race. And this is the rate for black women. Now, if I walk up to you and say, yeah, Twitter is abusive, you tell me, duh, I know that, everyone knows that, it's been since the beginning. If I tell you that black women are abused more, you say, that also makes sense, I expect that. But it's one thing to expect it and another one to actually see the number. The number is quite striking. And now suddenly, for the first time, you've put numbers on the issue. No one has ever measured the amount of abuse that exists on Twitter on a massive scale. Okay? And this is why all this momentum that Amnesty International has built now is even further amplified by putting some numbers. And what difference can that make? Well, let's see. I'm going to go back to the presentation, I hope. And, okay. Okay, let's see here. Now, after we released these findings, so this is what happened. A few hours later, well, the next day, several news outlets picked it up. For instance, we have here, Twitter is toxic for women, says Amnesty International. This is by Bloomberg. We have from Time, a toxic place for women. MIT Technology Review, this is the day after. Female black journalists and politicians get sent an abusive tweet every 30 seconds. Actually, they got it a little bit wrong. It's every 20 seconds. Okay. Wired. Twitter is indeed toxic for women. And the list goes on and on and on and on. I think I count about 70 of them there. So these are media outlets from around the world. Okay? And now I'm going to give you a little story here. So what you're seeing here in the time series is the share of Twitter, the share price. So on 18th of December, we released the study, and of course these articles came out. Day later, well, you get a little bounce. Price drops a little bit, as you might expect. And then this happens. So this is a newsletter that is an investment newsletter that is famous for citing all of the dangerous investments. That's what we call, it's like sour investments, hence the Citron name. And what the director said, that Twitter has become the Harvey Weinstein of social media. And then this happened. So we didn't expect that. There was a mediator, of course, and this amounts to, I think, $2.5 billion in losses. Now, if you ask me, what did I expect to do in my life 10 years ago when I went into this business, I certainly didn't expect to damage tech companies. But this is not really what we set out to do. We're not out to damage tech companies. We're out to enable human rights experts. So for us, this is the real impact. So the lady here on the right, Azmina, she was leading the campaign prior to this quantified study. And now here she's proudly reporting, she just attended a meeting with Jack Dorsey, who is Twitter CEO, with Amnesty's Secretary General. So immediately after the share price drop, Jack Dorsey reached out to Secretary General and said, well, we need to talk now. And so for the first time ever, through this quantified study, we managed to bring in the same table, Twitter and Amnesty International, so that they can find ways forward for transparency, for mechanisms to protect their user base, And yeah. So I want to spend a little bit of time just to talk a bit about the data and some of the challenges, the data science challenges that come with the study. A lot of you might think, well, where's the AI in this? Well, this is not about the AI. This is about measurement. This is about dealing with the biases that come with the data. You know, these are core aspects of data science. And as I mentioned, this is the breakdown of our cohort for 800 women. And here are some of the challenges. So one challenge that comes with the crowdsourcing is, now imagine you are a volunteer, right? And you're annotating this stuff. And the tweets, maybe you might encounter something like 1 in 100 abusive tweets. Now that sounds quite a boring task, right? And you know, you only encounter one abusive tweet in every 99. And you know, like, you don't feel like you're contributing much. So how do you deal with this potential fatigue that also leads to degradation of the annotating performance? So one way to do it is to artificially inject abusive tweets, tweets that are likely to be abused, to artificially inject them into the crowdsourced task so that to keep the task more engaging. The downside of that, though, is that now you've just artificially inflated all the abuse rates, right? So all these bars that I showed you would have been inflated. They're not accurate. So to undo that, you have to keep track of what is the percentage of tweets that you have artificially plugged in to keep the task more engaging. And then, you know, you compute some kind of weight, and then you can undo that by doing some kind of renormalization. So that's one bias. Another bias is that the question, how representative is the tweet coming in that day? You know, so the total volume on Twitter fluctuates. If you're a journalist and you're publishing an article, or if you're a politician, you're giving a talk or a speech, you know, there's a social context around the tweets. So people react, there's more conversation, there's more abuse comes with that. So any given tweet is going to have a different, is not going to be representative, the same way representative, depending on the day. So that is another kind of weight that you have to keep track of. And this is how we maintain all of these rates, we maintain them as unbiased as possible. And yeah, so I don't want to get into the details of that. Another aspect is disagreement. So any given tweet is, we looked at tweets that were annotated 3 times. Now, let's say this is a tweet, right? And you're asked, what is it, problematic, abusive, or no? You say, oh, this tweet is abusive. Someone else says, no, I don't think it's abusive. It is abusive. So these things happen, right? So there's going to be a lot of disagreement, and there is a way to quantify the disagreement. There is a way to get a sense of how hard is this problem, because abuse is very subjective. Some of the abuse is very objective, like the hardcore stuff, like life threats, death threats, rape threats, racial slurs, all the stuff everyone would agree that they're abusive. But there's some stuff on the gray area, like me telling someone, you're an idiot, I don't disagree with you. I mean, it's not constructive, but it's still toxic, right? So that would be a problematic example. And it doesn't really fall into any of the other categories that I mentioned. So one way to deal with this is, okay, let's just count the number of votes that were given in an interclass, and think of it as a 3D coordinate, right? Where the 3 different coordinates are the problematic axis, the abusive axis, and the no axis. And now we can think of all the possible arrangements that we can get for 3 annotators, all the different coordinates that you can get for a tweet, and then you take every tweet and you plug it into its coordinate. Now, in an ideal world, where everyone always agrees, by a miracle, this is what this distribution would look like. So think of this triangle. This is a simplex living in a 3D world. And it's flat because all the possible arrangements can lie on the surface. So in an ideal world, all of the tweets will fall into one of these 3 corners. In a world where everyone is voting blindly, so they're not really bothered to read the tweet. But at the same time, they make sure that the rate at which they select abusive or problematic agrees with the marginal distributions, the class distributions of the problem. So this is what the distribution would look like. This is equivalent to sampling from a multinomial distribution. This is in the real world. This is what happens in decoders. So you immediately see that, yes, even though in voting on the red side, you get a lot of mass at the top because everyone just agrees by random. In the middle plot, in the real world from decoders, we see that they tend to agree, but not only by chance. So there is, of course, there is actual agreement, and we also ran the same experiment with 3 experts. So 3 experts, 3 women that were working at Amnesty that have looked at a lot of tweets. They are also aware of a lot of the dog whistle politics that are happening in Twitter. They also looked at 1,000 tweets and they annotated them, and this is the agreement that we see. So just from a qualitative point of view, you can see that the experience of the annotators here, their training, plays an important role in how clean your data is going to be, how clean your labels are going to be. And these are just some ways to quantify the disagreement. So that, all these plots are more like qualitative and they're about visualization, but things like kappa, Kalaitzis kappa, and the ITRA cross correlation are some traditional measures people have used to assess the inter-rater agreement. So we did an interesting experiment, which was, we wanted to see if we use the expert labels as a kind of golden standard labels. We want to see, can the crowd predict what the experts think? So you use the crowd as a kind of classifier, I guess. And if you look at the recall precision plot, so precision means that if you say something is true, then it is indeed true. So that means that you have good precision. If I say something is abusive, it is indeed abusive. That's good precision. And recall is that how much of the abuse am I able to detect? So this is like a kind of trade-off. And in a perfect world, the classifier would kind of go like that. Okay? But instead, in this case, what we see is that the crowd source, the crowd, this is how it performs with respect to the experts. So this is very surprising, and it tells you that it's a really hard problem. How hard? Well, we also did the same thing we also trained some machine learning. We also trained some models. We wanted to see how well they predict the abuse. And I don't want to get into the details, but basically we took a BERT model. So BERT is a very famous language model produced by Google back in the day. And we took these, the embeddings from BERT that were available online, and we augmented them with abusive embeddings. So in a way, we kind of made a naughty BERT. And then we asked it to annotate all of his tweets and see how well it performs. And these are the performance plots that we get. And so they are at most as good as the crowdsourced workers, and they're quite on par with the human workers, which tells you that the workers kind of set the human assessment, the human judgment sets a kind of ceiling to the problem, and we cannot expect the machines to be better at assessing abuse. So they really kind of hit the ceiling there, which shows you how noisy this data is and how hard the problem is. Okay. So I'm gonna segue into the next topic. We also plan to release the data in as most unethical manner as we can by completely anonymizing the receiver of the abuse by just replacing their names with some ID, and also removing any mention of their literal names, so not just like the handles or the mention, but actually the literal names in every tweet. So this is to avoid any kind of to avoid victimizing any of the subjects or enabling, I guess, prosecutions. So this is what it means to release a data set Anyway, let's move on. So to a different topic, I also now want to talk about the case of Darfur. So Darfur is another case where Amnesty has been campaigning to raise awareness. In what's been happening in Darfur is for the last 15 years, the Sudanese government has been going around in rural areas, burning down villages, mostly from non-Arab communities. And the reason why this happened is complex, but it's partially driven by climate change. Yeah, because for centuries, these communities have been co-living, but now for some reason, they cannot. And this is one of the reasons, okay? So back in the day, before we existed as an AI for Good team, my research director, Julian Kornebish, when he left DeepMind, he was an independent. He did a pro bono project with Amnesty International together with Milena Marin and Daniel Worrell, who at the time was a PhD UCL, and Micah Farfor from Amnesty as well. And what they did is basically they did this experiment. Maybe I can play another video for you. Somewhere over here. So this is work not from Element AI. This is something that Julian did back in the day with Amnesty International. So they asked the decoders to annotate satellite tiles from a small strip of Darfur. And these are the tiles. So the task here is that you look at a tile, and if you find human presence, it's green. Okay? So they annotated all of the tiles along this very big strip, and then they trained a ResNet 50. So this is a kind of a staple for computer vision classification problems. Okay. So once you annotate all of that strip, then the question is, well, can you generalize out of sample? So you deploy it, you try it out of sample, and this is where you get all those red spots. And at a first glance, it looks a little bit hopeless, right? I mean, look at all these false positives, what's going on there? But if you zoom in, you actually see that there is human presence. Okay, and a lot of it is destroyed, actually. So the hallmark of destruction is a bunch of walls with no rooftops. And yeah, that's a little bit depressing. So even though they do care about detecting human presence does not imply destruction, but they only focused on human presence just as a proof of concept. And this shows you that machine learning, and in particular deep learning, is really good at computer vision, has this power to do planetary scale monitoring of human rights abuses. Okay? I'm gonna move on. Okay, enough of that. But this problem relies on high-resolution images. And the problem with high-resolution images is that they're really expensive. So remember those walls without rooftops? All of these are really high-resolution features. And if you cannot, one snapshot of the whole of Darfur costs millions of dollars. And if you want to do this kind of monitoring continually, for day after day or week after week, I mean, you can't do that if you're Amnesty. Like, you just don't have the budget. So, but there are low-cost, low-resolution satellites out there that have a high revisit time around Darfur. So let's take the case of some low Earth orbit satellites. For instance, we got Sentinel-2, which has 10-meter resolution. We got Landsat, 30 to 15. We got PROBA-V. PROBA-V is an ESA satellite. V stands for vegetation. And it was designed for the monitoring of vegetation. So not human rights, but environmental purposes. That one has a quite low resolution, but what is unique about that satellite is that it has two cameras on board. And one of them is low res at 300 meters per pixel. And the other one is high res at 100 meters per pixel. So think about that. So this is a unique situation where you have naturally occurring low-res and high-res imagery of the same thing. This is extremely rare in computer vision and super-resolution problems I'm going to show you. Okay, so we're presented with this opportunity here. We participated in this competition organized by ESA, and they gave us data, they provided data by ProbaV, and it was open to everyone, and people were asked, can you learn to super resolve? What is super resolution? So now I'm going to show you a little video so you can get an idea. Maybe some of you have seen CSI or Blade Runner.
Okay. Now let's get a good look at you.
Hold it. Run that back.
Wait a minute. Go right.
There, freeze that.
Full screen.
Okay, freeze that.
Tighten up on that thing.
Vector in on that guy by the back wheel.
Zoom in right here on the spot.
With the right equipment, the image can be enlarged and sharpened.
What's that?
It's an enhancement program.
Can you clear that up any?
I don't know. Let's enhance it.
Enhance section A6.
I enhance the detail and...
No, it doesn't have to enhance. Release it to my screen. Enhance the reflection in her eye. Let's run this through video enhancement.
Edgar, can you enhance this?
Hang on.
I've been working on this reflection.
Someone's reflection.
Reflection.
There's a reflection of the man's face.
Reflection.
There's a reflection.
Zoom in on the mirror.
You can see your reflection. Can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance it.
Zoom in on the door.
Times 10.
Zoom.
Move in.
More.
Wait, stop.
Stop.
Pause it.
Rotate us 75 degrees around the vertical, please.
Stop. Go back to the part about the door again.
Got an image enhancer that can fit that?
Maybe we can use the produce send method to see into the windows. This software is state of the art.
The eigenvalue is off.
With the right combination of algorithms. He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
Enhance.
Freeze and enhance.
So yeah, that was made in 2009 by a guy called, I can't say his name, sorry. But quite ahead of his time. So yeah, this is what we want to do. You want to get images like that look really blurry, and you want to enhance them. That was a gimmick. That's the only gimmick I'm going to show you today, I promise, okay? But yeah, so this is work that we call HiResNet, and it was done in collaboration with Mila. This is Joshua Benju's lab. We worked with a couple of interns there, a postdoc, and 3 postdocs. And from Element AI side, I was leading this research project. On Element side, we worked with Michel Dudon, who used to be part of the team, Julien Cornebiche, and Zichao Ling. So that was all fantasy, that was science fiction, but this is reality. This is what's happening in machine learning right now. So nowadays we have this wave of generative deep learning that can create content. They can create faces, realistic faces of imaginary people, faces that don't exist. Think about that. So it's really good at imagining stuff. In the same reasoning, you can also imagine what a low-res picture looks like in high-res. So let's say you take, this is what a typical super-resolution paper, single image super-resolution paper looks like in machine learning. You take some high-res image, you artificially decimate it. So this is what's called the downscale operator in signal processing. You basically blur and then decimate an image. So that's the low-res over there. And then you can do this about 1 million times for different images, and then you learn to reconstruct the original. Okay, this is like learning to super resolve by supervision. Like this is a typical supervised task. But this is single image. Now, and this is the prediction, okay, in the middle. So this is the output of a single image super resolution model. So a state-of-the-art model of that called SR-GAN. So GANs are famous for being able to generate content. And this is what the reconstruction looks like. It's pretty good, right? It looks very realistic. But I think the devil is in the details. Can anyone see what's wrong there? Just raise your hand if you spot what's wrong there, right? So you immediately, you might have seen that the detail in the scarf and the hat, they just don't add up. Like it's just It looks like a realistic texture, but it has completely missed what is going on. And there's quite a lot of stuff happening here. I mean, there's like a parade, you know, there's like horses, and there's a flower, and there's kind of snake-like texture. All the stuff is missed, because with a single image, once you decimate it, it's lost forever. You can never reconstruct it. I mean, you can enhance, you can make it look realistic and crisp, but you forever lost that very important detail. And if you are an analyst, if you're a forensic analyst, and you're relying on those high-resolution features for detecting destruction, you cannot rely on this type of super resolution. Because who are you going to show it to? How do you know that the model has not made up stuff up? Okay. What we're proposing, okay, yeah, so why is this hard? Let's take a very simplistic case in 1D. Let's say you take this wave, this is called a chirp wave, and it's basically a sinusoid whose instantaneous frequency is increasing in time, linearly. And it kind of sounds like that. And this is a natural signal, as you might encounter in nature, and this is a digital version of it, sampled at 1,000 times per second. And now this is sampled at decimated by 4, so 250 times a second. But then you immediately notice that there is this aliasing happening there. And the aliasing happens when your sampling frequency, the frequency at which you sample the signal, is not adequate enough to capture the natural frequency of the signal. So what happens is that suddenly this, the high frequency signal is masquerading, aliasing, as a lower frequency signal. And that's what's called aliasing. And what that typically happens when, for instance, you see some low-res images, digital images, you see some kind of like fences, they look a little bit weird, or sometimes you see the motion of the helicopter, it kind of like the blade is kind of staying still or suddenly going in reverse. That's because the shutter speed of the camera cannot match appropriately the rotation speed of the blade. Okay, so this was with single image super resolution, but what we're proposing is that using these very cheap satellites and the fact that they take multiple low resolutions of the same object, now we can combine these low resolutions to do the same task, super resolution. But now the difference is that this is not about creating imaginary content. This is about learning how to fuse. This is about learning how to de-alias the signal. Because in a low resolution camera, the same photoreceptor in a different revisit doesn't always get the same amount of light. It's always going to be, the signal is going to be aliased in a slightly different way. And you can exploit that. In fact, if the satellite happens by miracle to going exactly above the same point, you cannot do this. You need to have the slight differences. So I'm just going to show you some examples here. On the right side, you see a strip of a bigger picture of an actual ground truth high-res image. So imagine you're doing an agriculture monitoring application, and you really rely on recovering these road structures, which are example of a high-frequency feature, and the boundaries between the farms. But this is expensive. You can't do that. Instead, you can use these ones, which are free. But you don't get these features, like they're lost, they're blurred out, or they're lost they're aliased. But with our approach, high-resnet, now we can teach a neural network to fuse these things and recover some of the important features that we care about in our application. Just give me a second, let me mute that. Okay. Let's take another example. Here, another agriculture operation. So this is what's called pivot irrigation farming. And remember, every pixel here is 100 meters wide. So these structures, these pivots are massive. And you might be interested in estimating the yield that's coming out of these pivots. So again, this is high res, very expensive. This is low res, which is cheap. But you can't really make out much. It's like maybe you can say it's on or off. But once you combine them, then you're a game. Okay, that's pretty good. There's no fantasy. This is just fusion. Another example, you might be interested in recovering the path of the river. Maybe you're doing disaster relief applications and it's important to detect floods. Okay, so yeah. Okay, how does this all work? I'm going to use the remaining time perhaps to quickly go through, I'm going to skip through the architecture and I'm going to go straight into how all of this is applied for Darfur. Oh, by the way, we also applied it on the sun. Okay. And this approach was one of the top approaches in the competition. So we got like 2 leaderboards. One was the public leaderboard, and the other one was the complete leaderboard. And we lost by a tiny margin, actually. So anyway, these are the features that you want to recover, but these are really expensive, right? This is how you can assess distraction, human presence, etc. And now the idea is that what you see on the top 2 rows there is how well can you detect human presence if you rely on individual low-res images. Just take one low-res image and you try the same thing that I showed you in that video, in that demo. And the accuracy is not that good. So F1 score is like the harmonic mean between precision and recall, and you get 0.65, 0.68 if you rely on individual low-res images alone. But now if you go back to high-res images, this is the difference in quality. You get 0.8 in F1 score, 0.9 in precision. But what if we learn to combine multiple low-res images of the same area? It's somewhere in the middle, so 0.71 F1 score, 0.75 with a very decent precision. And the precision is important in this kind of application. So what does this mean? It means that suddenly you've unlocked a way that you can do detection of human presence with a decent precision. And now you can use this solution to basically kind of prioritize the areas that are the most likely to contain human presence or destruction or whatever. And then you as an analyst, you can go and say, now I'm going to order those top most likely areas, the ground truth high resolution from the satellite. So that can save you tons of money. So there's also, as I covered, there are quite a few environmental applications. I wrote a blog post a while ago with my colleagues called Computer Enhance Please. And it really lays out, it's a very accessible article, lays out our vision that we have for human rights monitoring and environmental monitoring through super resolution, multi-frame super resolution. So this is the end of my talk. Thank you very much for your attention.